pleasure to welcome Professor Petra Mutzel as our plenary speaker. Professor Mutzel works at the University of Bonn. She is Professor of Computational Analytics. She is also Scientific Director of the High Performance Computing and Analytics Lab at the Digital Science Center. Before joining University of Bonn, she worked at the Vienna University of Technology and after that at the TU Dortmund University. She holds PhD degree in computer science that she obtained in 1994 at the University of Cologne. And she worked as a postdoc at the Max Planck Institute of Informatics in Saarbrücken. In terms of her research interests, she focuses on algorithm engineering, algorithmic data analysis, and combinatorial optimization with various applications in graphs and networks. Currently, she is interested in chem informatics, and I hope we will soon learn what is this exactly, social and biological network analysis, statistical physics, and geodesy. She is a member of the steering committee of some of the very famous conferences in computer science, including European Symposium on Algorithms, ESA, ALENEX, and Valcom. She is associate editor of the ACM Journal of Experimental Algorithmics, Journal of Graph Algorithms and Applications, and Mathematical Programming Computation. I had a great honor and pleasure to have Petra also as my PhD advisor, and I have to mention that back 20 years ago, when she joined the TU Vienna, Vienna University of Technology, I think Petra was the very first female professor at the Faculty of Computer Science. Is that true?
Oh.
Full professor. We had an associate professor, but I think at that time, that was really something very unusual, hopefully, and luckily nowadays we see many more women in engineering and particularly computer science. This is great. And I really enjoyed this period working with Petra under her supervision. So it is a great pleasure to have you with us, Petra, today. I think we will learn a lot of things or a lot of new interesting applications in data science related to combinatorial optimization. So please, the floor is yours.
Thank you, Ivana, for your very nice introduction and very nice words. I think it's true. I was the first full professor there in Vienna, but there were associate female professors there already. Yeah, that's exactly true. So thank you also to Ivana and Francisco and Rita and Santanu for inviting me. It is a great pleasure to have the opportunity to present this talk today, which has the following aims. So first, I want to provide a brief introduction into algorithmic data science. Second, I want to give you an impression what we, so my research group and co-authors, are doing there. And third, I want to convince you that algorithmic data science is much more than only statistics, AI, or machine learning. And combinatorial optimization is an essential ingredient for advancing the area of data science. And you can also see it as maybe a call for participation. So our combinatorial optimization community should be more present and more visible in data science projects and activities, such as conferences and workshops. So when I look at these activities, I always see a lot of algorithmic people and a lot of course, machine learning and AI people, and only sometimes people from our community. And so I think there should be more. But let's start with data science. So this picture nicely visualizes what data science is about. It is about collecting, analyzing, and evaluating data. So these three little chipmunks do exactly this. The left one collects the small molecules from a molecule cloud. The middle one with the magnifying glass analyzes them, and the right one evaluates the analyzed molecules by assigning them to groups or clusters. At the end of my talk, you will know more about our work on Chipmunk. This is a virtual molecule library which has been published in this special issue of ChemMedChem. And so which was the basis for this cover feature. So we got the invitation to design a cover feature for this one. And so we decided to do it with the three little chipmunks. So, but let's first see, why is data science important? Why should we care as optimization community? Now, already in 2019, the ACM Career News stated data science is the America's hottest job, according to a Bloomberg article in 2018. And data science doctorates are drawing salaries up to $300,000 yearly. So in 2020, still Forbes said, data science is one of the hottest roles in technology today, but they also said, in essence, true data scientists are focused on broader issues of extracting value from data, while many who call themselves data scientists now are really machine learning engineers focused on ML, machine learning model development. So they stated that this is not enough. We need much more knowledge. So not only machine learning. So the ACM Career News now last year in 2021 stated it's still a job of the future. So the data scientist role also continues to increase in importance. So data science has topped the list of emerging jobs for 3 years now, and demand for this specialty will continue to grow across all industries for years to come. Now, still in 2022, it's the very first among the top 10 highest paying tech jobs in this year. So a data scientist, without a pinch of doubt, is the highest paying job across industries and sectors. And there has been a 29% increase in demand for data scientists year over year, and a dramatic upswing increase since 2013. So it's still a lot of money going in there. So there are also investments in Europe and Germany. So these calls are on artificial intelligence, which also contains a lot of data science. Yeah, in reality, they wanted the problems that AI should solve are data science problems. So, and there is a boost AI strategy made in Europe. So huge investments are to come into AI, and Europe wants to spend more than 20 billion euros. And also in Germany, there's an AI strategy of the federal government. So in 2018, there were planned investments of 3 billion euros until 2025. And 2 years ago, they stated that they will increase this to 5 billion euros, so almost double. And the focus in Germany is on sustainability, environmental and climate protection, pandemic control, and international networking. And so the focus is also on big data, on data science, and on digital transformation. So data science is a big part of this one. Now, the question to you is combinatorial optimization really relevant to data science? So why are you talking about this? We are working on some other problems, you may think. Now, I can just tell you my view for this. So let me introduce you now to the algorithmic data science aspects in my research. So in my view, a data scientist is curious about the secrets of the data to be investigated. He or she is creative and open for new ideas and has mathematical and algorithmic knowledge. And that's very, very important, of course, to put these ideas into practice. Yeah, and now many of you are thinking, oh, that's exactly what we are doing. Yeah, also the problems we have heard today, if it's the vaccination problems or the planning problems, they are all about data. We need to come up with some decisions and predictions and find some solutions. So all of us. So I do a lot of, for me, it's combinatorial optimization problems or graphs. That's my research I'm interested in. And so I do it partially using interlinear programming techniques, but I also do it, a big part on it is concerning algorithm engineering. So where we really look at the structure and talk to the users and try to find out what they really want to solve, and also look at the structure of the problem of the data, and then come up with better algorithms that scale better and have better qualities with respect to the really practical problems. And also some part of my work is in machine learning and AI. Now, in some of this work we will see today, so my research is really application oriented. So I have applications, as Ivana already said, in physics, in archaeology, in bioinformatics, in chemistry, in geodesy, and in neuroscience, very new now. Both of them, they just started now in Bonn. And we will see a lot of chem informatics. So Ivana, I can answer your expectations, hopefully. Or fulfill your expectations. Now, there's a very nice book. So if you want to learn something on data science or data analysis, I really suggest to read the book by Agarwal on data mining. And this one starts with the first section saying there are the 4 fundamental problems for analyzing data. And these are clustering, classification, and prediction, the association pattern mining problem, and the outlier detection problem. So if we, in many of the cases, one of the 4 problems need to be solved. Now let's look a bit closer into these. So clustering belongs to so-called unsupervised learning problems. And it's the task of grouping a set of objects such that objects in the same group or cluster are more similar to each other than objects in different groups. Now, there are many possibilities for formal definitions, and there are also many around. And the clustering problem has been studied for a very long time. It has started in statistics, I think already in the 60s or before that, then also in databases, and after that in machine learning, and now it's been studied in algorithmics and in the optimization community. It's very popular everywhere, actually. So it's useful also if you're dealing with big data, because it can be used for data classification and sampling approaches. So if you have the clusters, then it's easier to really sample specifically the things you want to have, the items you want to have. So the most popular approaches are distance-based approaches or centroid-based approaches. So K means clustering algorithm. I think everybody of us has heard this already before. So the classification problems belongs to the supervised learning problems. And here we have given a training set of items, of objects with labeled items, so classes. And the goal is we want to train a classifier so that a new item will be assigned to its correct class. So here in this left picture, we have, do you see my mouse? Ah, okay, thank you. So in the left picture, you have red and green labeled points, objects. And so you want to train a classifier. Here, the output is a predictive model. And now whenever a new item comes where we don't know if it belongs to red or green, then our predictive model should tell us the right class. And we can have 2 classes, so binary classification or many classes. That's a multi-class classification. We can have, so this is when we have discrete labels, and discrete labels, they are mostly studied in the machine learning community. And if we have continuous labels, then it's called regression problem. And this one is mostly studied, has been mostly studied in statistics for a very long time already. Now, also there are many variations of this. So there are decision problems or prediction problems. And popular approaches for these are support vector machines. So if you use, this is what we do, we use so-called kernel functions on graphs, so graph kernels, so that we use these ones. You can also use deep learning, which is also popular also for graphs now. And K nearest neighbors, you can also use K nearest neighbors, which we also did for some applications, and logistic regression, Bayes classifiers, decision tree methods, or you can also use clustering for this one. So there are many approaches also there. Then there is the so-called association pattern mining problem. So here the goal is to find inherent regularities in the data. So you may have heard about the frequent pattern mining problem. That's more popular than the associated pattern mining problem. So for the frequent pattern mining, we want to find frequent items that occur. Frequent items are ones that occur at least some minimum support number of times. And the generalization of this is the so-called association pattern mining problem, where you also take association rules like this one into account. So so this one is also widely studied in data mining, which is also studied many years ago. And it's useful for deriving similarity measures on data sets, but it's also useful if you want to solve the clustering problem or the classification problem or the outlier detection problem. An outlier detection problem is also, everyone has seen this already before. So here we want to find data items that are different from the majority of the given data. So here we want to find the red fish in the ocean of the blue fishes. So an outliers may reflect errors in the data, or they may belong to rare events. That's the reason why I want to find them. And the methods are statistical tests, so that's in statistics, are models based on spatial proximity, so like k-nearest neighbor approaches, or density-based methods, and many others. And you can also solve it using clustering, classification, or the association pattern mining problem. So you see the four problems, they really are connected to each other. If you know how to solve one of them, you also know how to solve all of them. And Agarwal then stated at the end of this very interesting section that an important basis for all of these are distances and similarities. Of course, if you want to compute a clustering, you need to have a notion of when are 2 points similar to each other and when are they far apart. And so for points, this may be very easy. Here we see, okay, these red points, they are all close to each other. But if we consider now graphs, it's not so easy, because a graph is not a point in some high dimensional space. And now, so that's this is what my talk is about today. We want to find notions, or to discuss some similarity approaches on graphs. So here we have two graphs, and if I ask you, so when are these two graphs similar? It's not so easy. So there are some similarities in these graphs. Now, what do you think? Yes or no? And for these two graphs now, it's even harder. It's not clear to us if they are similar or not. Somehow they are similar, somehow they are not. And of course, it's clear that if you want to get an answer to this problem, you always need to have some use case. What is the question you want to answer with this? What is the problem you want to solve? So you also need to look at the use case you have, at your user, at the practical problem. And it also always depends on the remaining graphs in your class. If the remaining graphs are also always look very similar to this one, then this one may not be so similar. But if the graphs are very different, then these two graphs may be very similar. So, and this is our plan for today. So we are done with the introduction. And so the main block today will be a discussion about the approaches to graph similarity. So I will start with isomorphism-based approaches, and then we will go to distance-based approaches and to embedding approaches into feature vectors. And then we will see how to apply these approaches to data analysis, and we will end with some outlook and conclusions. But before we can look to graph similarity, we need to look at what does it mean that two graphs are identical, are the same to each other. And this is what graph isomorphism is about. So I want to start with section 2 with graph isomorphism. Now here we have let's formally define the graph isomorphism. So we have given two graphs which are simple, and we have then a bijective mapping pi from the vertex set of G to the vertex set of H is called a graph isomorphism if the following holds. So whenever we have two vertices in the graph G, which have an edge in between, then there also must be an edge in between to the mapped vertices of this one, and vice versa. If we have an edge here in the map, then we also need to have an edge in the original graph. So this is an if and only if relation. Now here I have colored the vertices, the mapped vertices, the mapping, so that it's easier for you to see that this one is indeed a graph isomorphism, and these two graphs are really identical to each other. So two graphs are called isomorphic to each other, and this is the notion here, if a graph isomorphism exists between the two graphs. Now I want to ask you, are these graphs isomorphic to each other? What do you think? Yes or no? They look very similar, but maybe not exactly. So it's not easy. So if your answer is yes, then it should be easy to come up with an answer. You just give me the mapping and it's easy to see, to check this answer, yeah, if your answer is right. But if your answer is no, then it's not so easy. How will you prove to me that these two graphs are not isomorphic to each other? Essentially, you must enumerate all the possible mappings, and this can be quite, take a lot of time. And if you have graphs like this, then it's even harder to decide if these graphs are isomorphic to each other. So later in my talk, we will see the answer to this question. Now the graph iso, so we have looked at the graph isomorphism problem already. So we've given two simple graphs, and we want to decide if these two graphs are isomorphic to each other. Now the graph isomorphism problem is one of the very famous open problems, still open problems, where we don't know if the problem is solvable in polynomial time or not. So recently the Babai came up with a quasi-polynomial algorithm, which is the best running time known so far. But yeah, it's still not a polynomial running time. So this is the theory. In theory, the problem is, we don't know something about the problem. That's really an open problem. But in practice, if you give me two graphs, then almost always the graph isomorphism problem is solvable very fast, very quickly. So you can use, for example, the Weisfeiler-Lehmann algorithm, which we will see later in the talk, or use any one of there are many tools around, Naughty or many other tools around for solving this. So in practice, graph isomorphism is very easy, and in theory, it's hard. But our interest is not in graph isomorphism if they are the same, but our interest is in how similar are two graphs. So, but we will start with the isomorphism-based approaches. So the first idea, and the idea of the so-called maximum common subgraph problem, is to say that two graphs are similar if they have large parts, large subgraphs that are similar to each other. And then we say that these graphs are more similar than other parts. So the definition of the maximum common subgraph problem is as follows. We have given two graphs G and H, and we want to find the largest vertex sets R in G and S in H, such that the induced subgraphs G of R and H of S are isomorphic to each other. So here you see in blue colored the two graphs we have just seen before, which were isomorphic to each other, and the yellow part, which I've just added. And so you can easily see, or obviously find out, check that the blue parts from G and from H are indeed corresponds to the largest common subgraph of these two graphs. So here, if we want to solve this problem, then the complexity is, we know that the decision problem of this problem is NP complete. So we know that this problem is really hard to solve. There are many variants of this problem, so you can consider vertex or edge-induced subgraphs or without induced, and it's widely studied in, this problem is widely studied and used in cheminformatics. And why? We will see this now. So that's the motivation for the cheminformatics. So we worked on rational drug design. So here the pharmacists or chemists like to answer questions like, which molecules are active against some disease X? Or which molecules have a similar function or effect as another one? So this is an interesting question if you want to reduce some side effects or you want to increase the effectiveness of some molecules. Or sometimes you have the databases and you just want to do a high throughput screening for promising candidates. Now molecules can be modeled as graphs with attributes. So here you see that is one that is very easy to do this. So each atom now gets a vertex, and you can come up with labels on the vertices and labels on the edges. So it's very directly possible and very easy. And this also works, and that's the reason why the chemists really use it, because there's a direct relationship between the structure of the molecules and the effects of the molecules if you use it as a drug. And this is where a graph similarity comes into account. And also the chemists have worked many years on this. And this is a project within the German Science Foundation, within the program Algorithms for Big Data. And it's a project jointly with Oliver Koch, who is now in Münster and just got a Heisenberg professor there. But I have told you that on the one hand, this problem is very hard, but on the other hand, the chemists are using it. So how does this go together? Now, this is because the molecule graphs, they have very nice properties. So many of them, so they are very tree-like. So they are almost always planar. They are often outer planar. They have a bounded tree width. So they look very, a lot like trees. And they have bounded degree, because you see the degree is mostly 3, and I think the maximum degree is 5 or 6 possible degree. And so these are graphs that have vertex and edge labels. And of course, if you now look at graph isomorphism, you need to take these vertex and edge labels into account, which is done also. So, but nevertheless, the problem is still hard. So there are polynomial time algorithms for trees and outer planar graphs, but it's already NP-complete for partial K trees, for K equal to 11 with bounded node degrees, even if the node degree is bounded. So partial K trees, so think about the graphs with tree widths at most 11, and then, or from 11 on, it's NP-complete. And we have also shown that it's NP-complete. The problem is NP-complete, even if you restrict your graph class to partial 2 trees, if you're looking for bi-connected components, and if almost all the vertices of the have a degree bounded by 3. So it's still very difficult, this problem, but if you look at the problem, what the chemists really want to solve, they want to see, for example, what is the similarity between this sildenafil and vardenafil. And if you look at this, they are interested that the rings and the bridges that they are preserved in your mapping, in your graph isomorphism, in your map. So if an edge is part of a ring here, then it should also be part of a ring here, because the rings and the bridges here, they have very different roles in such a molecular structures. So we have not the normal classical maximum common subgraph problem, but we have the so-called block and bridge preserving maximum common subgraph problem. And this is really very important in cheminformatics. And of course, also the cheminformatics scientists have looked at this problem before. But there were results only for trees and outer planar graphs. So if your molecules are trees or outer planar, then were polynomial time algorithms known, and we could generalize this to polynomial time algorithms for this block and bridge preserving problem for partial 2 trees. So this is much more than outer planar. And the idea of our approach was to use a decomposition into block and cut trees and into a decomposition of the graphs into so-called SPQR trees. So, but let's go to distance-based approaches. Now, a very popular approach, which is used very widely, is the graph edit distance. This graph edit distance. So the idea here is you have given 2 graphs, and you like to transform the graph G into the graph age, and you are allowed some certain operations. So here mostly the set of permitted operations is to insert new nodes or edges, to delete nodes or edges, or to substitute nodes or edges. Now here we have, if you want to go from the left graph to the right graph, we have deleted node N1 and the edge E1. We have deleted edge E2 and we have introduced the new edge E4. And we have introduced the new node N2 and introduced the edge E3. And now you can assign costs to every such operation. You can say, okay, if we introduce this node, it costs like this much. And if we introduce or delete this edge, then it costs only this much. So you're very flexible in the costs with your choice of costs. And this is the reason why this approach is very, very, very popular in cheminformatics and bioinformatics. It's very often used. But the graph edit distance problem, so you like to, of course, to find the minimum cost transformation. This is NP hard and it's even APX hard. So there is no, there is no constant approximation algorithm for this problem unless P is equal to NP. But what they are doing, so what the scientists are doing there, they just use some heuristics, some greedy heuristics or some other heuristics in order to solve the problem. Now there are also exact approaches to this. So there are integer linear programs and there is also a graph approach. So of course you can model a graph, come up with a graph where every node in the graph is so you start with the left original graph G, and then you come up with all possible operations, which are possible single operations. And these are your new nodes. And from these nodes, from these graphs, you come up with new operations and so on. So you get a huge graph. And in this huge graph, you solve the shortest path from G to H. And for this you use the so-called A-star algorithm, which is a very successful shortest path algorithm. But because of your graph is so huge, you can both exact approaches currently work only for very, very small graphs. So it's really bounded by the number of nodes is 10, bounded by 10 or 15, something like this. So it's really not working in practice, this approaches. But I find this very interesting. So I decided to, in future, to look at these approaches. We are also looking at this because of a new project we started in Bonn with some colleagues from geodesy, and they are interested in the dynamic sea surface reconstruction. So they are interested in the seasonal variability of the sea surface, and here you see the North Sea. The North Sea. And so the data they have here are records from so-called tide gauge measurements. These data are very sparse because these tide gauges are only at the shores of the seas mainly. But this data is available for a long time, since 1900 already. And since 1993, there are also satellite altimeter data. This data is very dense, but they are available only for the last 29 years. And the goal now is to learn a reconstruction of this dynamic sea surface by combining both data sets. So we want to use one of the tide gauge measurement data sets in order to come up with a triangulation, and then use this triangulation to interpolate it with the newer satellite data for some months. And the other way. We want to use a triangulation for using both data, the tide gauge data and the altimeter satellite altimeter data which we have only for the last 30 years. And then we want to come up with a triangulation for this. And then we want to use this triangulation in order to come up with a reconstruction for the years before we had the satellite data. And so for this, we also need to compute some similarities between two triangulations. And for this, we use a special case of graph edit distance, which is called the geometric flip distance. And we started to work here already with our colleagues from Bonn. Now, another approach is based on distances is the so-called Frobenius distance. And here the idea is so permute the vertex set of G so that the number or the cost of the edge mismatches with respect to H is minimized. So the idea is that every graph can be represented as a matrix. And now we want to permute the set of rows and columns of the matrix, so that if you take the permuted matrix here and you lay it exactly over the matrix of your second graph, that then if you then take the mismatches or the difference in the costs, that then this, if you sum up this one, then that this is minimized, and that's the so-called Frobenius distance. Now, Martin Grohe, Gaurav Rattan, and Gerhard Wöginger, Gerhard Wöginger unfortunately passed away some weeks ago. They have shown that this problem is also NP-hard. But also this problem is used in as a model in visual computing. So we have a very young colleague now in Bonn who has worked in computer graphics, computer vision, and he uses this distance for his shape matching approaches. So here you see some matching between the two facial, between the so-called correspondence points these scientists use. Now a third approach, and this is also where I've worked a lot, is the idea to embed the graphs into a so-called feature vector. Now here the idea is to encode the properties maintained under graph isomorphism into a vector. So examples are the presence of special small graphs. So here we have two graphs, G and H, and here we just code if the graphs have a green labeled vertex or not. So G has one, so it gets a 1, and H has no, so it gets a 0. And you do this for all kind of small graphs you want to, you can enumerate it or you are interested in. And so for this, you get a feature vector now from your graph. You have made a so-called feature vector. And now you have a vector from your graph, and now you can use all these very nice vector approaches, existing vector approaches for points. You can also use the properties of paths, cycles, or subgraphs, and you can also use the eigenspectra of the Laplace matrix. So this approach has been used quite, it's also very popular in graph learning and also in graph learning. And it's often used for social network analysis and also in cheminformatics and bioinformatics, because the molecules that we have seen are very small, and here you can enumerate the set of all triangles, the set of all cycles of length 4, and so on. Now, but a better for graph learning is really to use a Weisweiler-Lehmann algorithm for this. So to construct feature vectors by the Weisweiler-Lehmann algorithm. And how do you do this now? So here you see the original graph G and H. And the idea is now initially all the vertices have the same color. So all the vertices are yellow. And then the algorithm proceeds in rounds. And in each round, we further separate identically colored vertex sets based on the color histograms of their neighbors. So for each vertex here, we look at their neighbors. So this one has 2 yellow neighbors, this has 3, and this has 1 yellow neighbor. So the 3 of them get different colors. And this has, again, 2 yellow neighbors, so these 2 can stay with the same color. And then we start with the next round. Now this one has a yellow and a red neighbor. This one has a yellow and a red neighbor. So we end up, because nothing changes, so we can stop the algorithm. And for H here, it looks different, because this this vertex has 2 yellow neighbors, and this one has a yellow and a red neighbor. So these 2 get different colors, so we get a blue color to it. And again, so how do we now construct the feature vector? So we just add up, we just append all the histogram vectors after each other. So in the first round, we had 4 yellow colors for G and 5 for H. In the second round, we have 2 yellow colors, 1 red, 1 green, and so on. So, and we can also weight these rounds differently. So we can often, we say the first rounds, they are much more important than the later rounds. And so this constructs a feature vector. And again, we have made a vector out of our graph. So this approach is very popular and it's also very successful in graph learning. So that's very consistent. So if you're looking at all the papers and if you compare all the approaches, then Weisweiler-Lehmann is almost always among the best ones. So what are the properties of the Weisweiler-Lehmann algorithm? So if two graphs get different colors, then we know for sure that these two graphs cannot be isomorphic, because if our two graphs are the same, then we must end up with the same colors. And if you give me two random graphs, then with a high probability, the colors will be different. And so with high probability, we will identify the two graphs that they are not isomorphic with high probability. But there's also some problem with it. So if we have regular graphs, then of course Weisweiler-Lehmann cannot do anything because it stops already after the first round. Because if every vertex has the same degree, then all the neighbors get the same color. All the neighbors are the same as 2, 2, 2, 2, 2, 2, 2, 2, 2, and we cannot distinguish regular graphs. So this doesn't help. So this is why the people then decided to come up with the so-called k-dimensional Weisweiler-Lehmann version. And there are many, many versions of this one, and I just show you one of them, which is based on k-vertex sets. And so here we say that so we build the set of all k-sets of the vertices of the graph. And we say that two k-vertex sets are neighbors in the k-set if they differ in only one element. So for this graph here now, we build a set of all two sets, which you see here. And two sets are neighbor to each other if they differ by only one element, which is true here, but which is not true for UW and VR. So they differ in two elements, and therefore we have no neighbor in this. They are not adjacent to each other. So now we have built the so-called k-set graph. And now on this k-set graph, we can start an original Weisweiler-Lehmann approach again, algorithm approach. But we need to change the very first, the initialization. For the initialization now, we have to consider k-sets. And we say that the k-sets, two k-sets get the same color if the graphs that are induced by these node vertex sets, they belong to if they are isomorphic to each other. So this U and V and U and R, U and V has no edge. The induced graph just has two vertices, and the induced graph of U and R has two vertices and the edge. So they are different, and this is why they get different colors here. So you start your Weisweiler-Lehmann with this coloring, and then you do exactly the same as before. You just further separate identically colored vertex sets based on the color histograms of their neighbors. So, and if you do this, of course, you can be stronger than before, and you can solve the problem with the regular graphs. So what are the properties? Some properties of the k-dimensional Weisweiler-Lehmann. So if you increase the k, you get stronger, which means that more graphs are identified, which means that if you're given two graphs, that you can decide that these two graphs are not isomorphic to each other. This one, of course, if you choose k large enough, so if you choose k equal to n, then you can solve the graph isomorphism problem. But remember, in the very first step, you need to solve the graph isomorphism problem, so that doesn't help you. But you can choose a k of order of log n, and this is what Babai's quasi-polynomial algorithm for the graph isomorphism algorithm does. And you can do this, and 2 the power of order of log n is still doable, and in theory at least. And so this is what Babai does, but it does much more. So he really uses very deep algorithmic, deep algebraic theory and group theory. And it can be shown if you want to restrict yourself to the k-dimensional Weisweiler-Lehmann approaches and you want to solve the graph isomorphism problem, you cannot do this. You need to choose k of order of theta of n. So, and here we can see that the k-dimensional Weisweiler-Lehmann can indeed distinguish regular graphs. So for this graph here, we get 2 color classes, and for this graph here, we get 3 color classes. So it's strong, the k-dimensional Weisweiler-Lehmann is strong for higher k, but it's also very slow, because if you look at this, you need to come up, if you have n vertices, you have n to the power of 2 vertices in your graph, and if you are, and you see that these graphs get very dense also. And this is why we, a few years ago, jointly with Christopher Morris and Christian Casting, came up, suggested a so-called local version. So the k-dimensional local Weisweiler-Lehmann, which restricts these edges you have in this k-set graph to local edges. And so I cannot give you the definition now, but here we could show that the local version refines at least as much as the global version. And here you see the difference for this graph here, for example. This is the classical global 2-dimensional Weisweiler-Lehmann on the sets. And this is our new local version. And here you get only 5 color classes, and we get 10 color classes. And you see that it's even much faster, because you need to check the number of neighbors here is much less than the number of neighbors here. Now, there are some famous graphs, and these are the gadgets we have seen before. And if we are using the 2-dimensional Weisweiler-Lehmann, we get 4 color classes only for both graphs. So the classical version cannot distinguish these 2 graphs, and but our local version really can distinguish these 2 graphs. So we get 5 color classes for this one and 11 color classes for this one. So we have, this is a proof indeed, this is a proof that these 2 graphs are not isomorphic to each other, and this proof is very fast. Now, recently we have shown that at NeurIPS, we have shown that the discriminatory power of our new local version, which is the blue shown here, is indeed at least as good as the discriminatory power of the yellow, the classical one, and the green one. And these were all versions which were there before, and all of them, they take much, much longer than our version. Now, there are very, very nice connections to descriptive complexity and to k-pebble counting games and to counting homomorphisms. This is why algorithmic people or theoretical computer scientists working on logics are very interested in this approach also. But we may be interested, if we work on combinatorial optimization, we may be interested in the relation to Shirley-Adams relaxations of the natural integer linear program for the graph isomorphism problem, and to the relation to the Gribner basis. And there's also very natural relation to graph neural networks, which are very popular, used for deep learning. So if you want to know more about this, then you can just ask Martin Grohe from RWTH Aachen, or read one of his great books on this or papers. Now, how do we now apply these? Now, this is easy. We have seen that we have made from all of our graphs, we have made a feature vector now. And now every feature vector now corresponds to some point in some feature space. And the idea is now that in this feature space, if this feature space is high dimensional, that now graphs who are similar to each other, they are closer in the space than other graphs. So we generate this feature vector for each graph in a data set, and now we can apply our favorite approach for learning on the point sets. So for example, graph kernels via the support vector machine, which we have done, graph neural networks, k-nearest neighbor, or the Jacquard coefficient. Now, now you can do, for example, classification with distance-based approaches. So the idea is to compute the distances, so the inner products of the feature vectors for each pair of graphs in the data sets. And then we compute one or more separating hyperplanes in a high-dimensional space. And this is what we have done. And these are some results on some benchmark data sets, which are in protein interaction networks, social networks, or cancer data sets. And so these are here you see the quality of the classification results after some tenfold validation. So what you do is you distribute your data set into 10 parts, and you take 9 parts of them for learning your data, and then you take the last part in order to check and to see how good is your classification. And so this is the result here. And the green one is the classical, so the higher, the better. The green one is the classical Weisweiler-Lehmann approach. The yellow ones are the classical k-dimensional versions, and the blue ones are our local versions. And you see that our local versions work much better on many data sets. And they are also much smaller. They need much smaller, they are much faster than the yellow classical ones, k-dimensional ones. Now we've used this for classification, for the recognition of the, now the time is over. For the recognition of digitized cuneiform characters in archaeology with our colleagues from the TU Dortmund. We've used it for new similarity measures for the human adhesion protein network complexes. This was mainly with the group of Sven Rahman in Dortmund, who is now in Saarbrücken. And we have recently used it for the classification of dissemination processes in so-called temporal graphs. These are graphs that change over time. So here, for example, you can use, you can find fake news in Twitter networks or so. And you can also use it, we haven't done it, but we want to use it for classification of brain data. So there is currently a lab running, class running, jointly, a project running jointly with with Dr. Kobeleva from the University Clinic in Bonn, where we want to use functional MRT data for classifying these data they have. Now we also used the subgraph isomorphism similarity for clustering a set of graphs. So here we have given a set of graphs, so think of molecules, and we want to find a clustering that maximizes cluster homogeneity and separates the cluster from each other. And the setting in our drug design was we had small graphs but a huge number of graphs. And so, for example, our graphs look like this. And so if you use our maximum common subgraph approach, then we get clusters which look like this one here. And here you see the graphs from the beginning. And so in our use case, they end up indeed in the same cluster. Now you can use this, so this was part of our project, Grab a Drug, on rational drug design. So we also came up with a tool, the scaffold hunter tool, which can be used for the explorative analysis of molecule databases. We can search for similar molecules, and it was used to create a virtual molecule databases for drug design. And so we designed the library Chipmunk with it, which has 95 million of molecules with up to 700 atoms and 90 attributes per atom. And this is where, this is what we published in this Chipmunk, what we published in ChemMedChem, where you saw the 3 little chipmunks in the beginning. Now, the outlook, of course, there's always, it's a very nice playground between the expressiveness and the generalizability for graph similarity. So you really must look at your use case and then decide what you want to have. You must integrate the expert knowledge, and this is what many people are working on in the moment. We want to integrate in uncertainty, that's also an open point, and the integration to temporal graphs. There are some approaches, we've worked on that, but there's a lot to do here still. So I like to conclude. So I hope that I got you interested in the area of algorithmic data science, and that algorithmic data science really needs a lot of combinatorial optimization, and there are plenty of opportunities for new theoretical results as well as practical impact. So I want to end up with my call for more participation in algorithmic data science of our community. Thank you very much.
Thank you very much, Petra, for this excellent presentation. we still have time for questions. We have about 5 minutes. So please either raise your hand or type your questions in the chat or in the Q&A part, and we will turn also your microphone on if you want to ask your question in person. While we're waiting for the people to start with questions, it is really a little bit disappointing that MIP-based methods are so unsuccessful. The mixed integer programming, that it doesn't really work for these problems, right?
I'm not sure that our community has worked a lot on it. I didn't find many papers on that, so I think there's plenty of opportunities to improve on this.
So you think that it doesn't have to be so pessimistic as it looks right now?
No,
right. Okay.
No, because if you also if you also have your use case in mind, you can even improve on that. But I see a question. Yanis Kurz has raised his hand.
Okay, Yanis, please, the technical chair, maybe it can turn on.
Maybe you cannot yet see it. Yeah.
Yeah.
Can you hear me? I think.
Yeah.
Yes.
Perfect. Yeah, thank you very much for this interesting talk. So my question is, so if you have a graph where you have weights on your edges and maybe even on your nodes, so let's say you want to compare an instance of the shortest path to another instance or calculate the distance. So is this Weisweiler-Lehmann approach easily adaptable to this case, or do you need a totally different approach to extract features?
Okay, if you have discrete labels on your edges, then you can use the Weisweiler-Lehmann. But of course, if you more are interested in shortest path, then you should use the shortest path kernels, graph kernels. So there's also a lot of work on walk kernels and shortest path kernels. And if you have continuous attributes on your edges, then Weisweiler-Lehmann so far does not work. And there's a very nice survey paper by Borgward. So if you search Borgward and graph kernels, there's a very nice book or a very thick paper on it. They really compared all possible graph kernels with the graphlets I showed you and the Weisweiler-Lehmann approaches and the graph path kernels. And they come up at the end with a very nice diagram. If your instance looks like this, then use this, and then use if you have this labels, then you use that one. But on almost all way down the diagram, Weisweiler-Lehmann is one of the approaches he suggests. But if your labels are not discrete, then you cannot use it so far. Yeah. There are approaches. There is an approach. Also, Christopher Morris has suggested you can do some hashing, sensitive hashing. There are approaches, but it's not directly. It cannot directly be used. But if you're interested in paths anyway, then I think shortest path kernels or centrality approaches are more interesting for you.
Okay, thank you.
Okay, other questions? And I don't see anything in the Q&A. Please feel free to raise your hand. Otherwise, I was wondering, I think the approach is based on calculating the maximum clicks on the association graphs for solving the isomorphism problem are also successful, right?
Yes, yes.
And what about now not looking for the question of finding whether the two graphs are isomorphic, but finding the maximum common subgraphs? Are they as successful for this problem or not? The click-based approaches.
Yeah, they are also success. So we are also using them for our cheminformatics approach. So our polynomial time algorithm has a running time order of n to the power of 5, which is quite high. So we use the click-based approach indeed. Yeah, you're right.
Okay, so. And the Weisweiler-Lehmann, as far as I understood it, is actually used only to give you the answer yes or no, whether the two graphs are isomorphic or not. Or
no,
can you also, yeah?
You get a feature vector.
Yes. Okay. And then based on the feature vector, you can still find the subgraph. Okay.
Yeah.
Okay.
But but you don't get a structure. So you lose the structure of the graphs. Yeah, that's a big difference. This is why for drug design, the structure is more important. This is why we use the maximum common subgraph approach there. But for social networks, the structure is not so not so important. So it really depends on what you want to solve. Yeah.
I see. Okay.
You lose the structure. Yeah.
Thank you very much, Petra. If there are no further questions, then thanks again. The talk has been recorded. It will be posted online also for the future learning and for the potential applications for people from our community. I think that is really very interesting and useful. Thanks again for being with us and to all participants as well. And we will now have half an hour break and we meet again at 4:30 for the final 2 parallel sessions and then at 6:30 for the closing session with the closing plenary. Thanks again.
Thanks for your attention and also thanks Ivana and to all of you to the organizers for inviting me. It was really a pleasure to give this talk.
Thank you.
It was also a pleasure to meet you again, Ivana.
And hopefully in person soon.
Yeah. Oh, yes. Yes.
Okay. Thanks.